Good morning. Today we are going to discuss something about heat affected zone and its characteristics in welding. Heat affected zone. And its characteristics. Normally heat affected zone will be called as HAZ. So, in welding, the primary part, the weld joint, are this is your weldment where we have a complete fusion of the weld metal, and a small area of the weld metal which is being highly affected by the heat of the welding process. So, this is normally called as heat affected zone. Why it is? Because in this region this shall be called as fusion zone FZ, and this is your HAZ. Here the fusion zone will have a complete melting of the metal. Fusion zone will have a temperature range above melting temperature of the material, melting temperature, and it is being called as normally Tm. And the heat affected zone HAZ, normally it will influencing the temperature in the range of above A1 in case of steel, above A1 to that is melting temperature Tm. Here one has to understand what is the reason behind to study about the heat affected zone of welding, because in the weldment we will have a complete control over this, because once we can select the filler material or we can add any alloy element by which I can able to control the weldment property. But irrespective of the weld metal, that is called your filler material, and irrespective of the welding process which we are choosing, this heat affected zone is unavoidable in any kind of welding process. And why we need to study about heat affected zone? Because of two reasons. One is it can alter the microstructural changes, in the zone, and secondly it can pick the hydrogen pickup, and later it will create a hydrogen induced cracking. The first one is microstructural changes in this region, and the second one is hydrogen pickup both in weld metal and in heat affected zone. Due to this reason, due to the pickup of hydrogen, it will create a crack at the later stages. So, the fusion zone can have a chances of controlling, whereas the heat affected zone can have a minimum control over the microstructural changes. And when I am considering the property of my joint, weld joint is proportional to the and depending to the both fusion zone and the heat affected zone. So, it consists both metals property. So, we can expect some kind of microstructural changes in the heat affected zone, and there is a possibility of hydrogen pickup. So, because of these two reasons, one has to understand what happens in this zone. So, now we will try to find what are the various reasons. So, before understanding what are the various microstructural changes in the heat affected zone, one need to understand why this was happened. Since this is your weld metal, this is your fusion zone, and if we fix some thermocouples in between some distance away from the weld metal, maybe 1, 2, 3 and 4, definitely this parent material will be experiencing a different kind of peak temperatures with respect to the distance. That can be drawn with the aid of some temperature profile lines. This is your temperature and this is your time. This is your peak temperature line. This is the locus of peak temperature curve. Now, this may be the temperature is range less than A1 and this may be this is your A1 and this is your A3 and this is your TM, melting temperature. Now, the zone 1 will experience a very high temperature which is nearly equal to the melting temperature of the base material, and zone 2 will experiencing above A3 temperature, and zone 3 will experience just above A1 and below A3, and zone 4 will experience a temperature which is less than A1 temperature with respect to iron carbide equilibrium diagram. Now, this is your real heat affected zone, because we know very well in iron and steel material will experiencing a phase transformation in between above A1 temperature, that is called your critical temperature of the material. So, now this weldment which is of steel microstructure will definitely experience a very high temperature which is greater than A1 and which is up to melting temperature will have a phase transformation and will experiencing a very high temperature. This zone of the material will definitely undergone a phase transformation. This is your heat affected zone. So, irrespective of the process selected and irrespective of the filler material used, irrespective of the material which is being subjected to welding, we are unable to avoid this kind of changes in a particular region of the base material. Heat affected zone by definition, the parent material which is being highly affected by the heat of the process, which is not really expected by any welding engineer or any people, or even heat is being transported from the fusion zone of the weldment. From the fusion zone of the weldment, heat is to be transported this direction. So, this material with respect to different distance have to experience a different peak temperature. Due to that peak temperature, this material will have a different microstructural changes. So, now we will compare with the iron carbide equilibrium diagram how the microstructure is changing. This is your A1 line and this is your now, this is your A1 line and this is your A3 line and this is your peritectic point. And this is your A1 where we have the temperature in a range of 7 to 7 and this is 912 and this is peritectic 1492 and this is above liquidus where we have complete liquid here and this is your complete gamma and this is your alpha plus gamma. And this is your alpha plus Fe3C. And now with respect to temperature, 539 is the melting temperature of steel. Now we can compare the microstructure of the weldment with respect to this iron carbide equilibrium diagram, and we can easily subdivide the heat affected zone into different zones. This is your weld metal, that is called fusion zone, and away from that you will have a partially melting zone, that is called recrystallized, that is called partially melting zone. The temperature in the range of above peritectic temperature and below liquidus temperature, this region will have a partially melting zone. The temperature in the range of above peritectic and below liquidus temperature, and this region, a complete metal will have your fusion zone in this above liquidus temperature, and below peritectic and up to A1 will have a different zone of parent metal. This is your interest. This is called heat affected zone. And now below A1 temperature, this is the zone where is your parent metal, unaffected parent metal. Now with respect to this iron carbide equilibrium diagram, we can able to understand in the heat affected zone the temperature is ranging between 727 to 1492. So definitely we can expect different kind of phase transformation in between with respect to the steel metallurgy. And now we will see, can one compare the heat and the thermal cycles which is related to the heat treatment process of the metal? Yes, we can compare, but the thing is there is a small difference between these two, that are with respect to only thermal cycles. With respect to only thermal cycles, in welding process the heating is sudden and it is having a very small time, and it is being cooled to room temperature in minimum time. As compared to the heat treatment, heating is slow and progress and holding for some time and cooling in a different cooling rate with respect to the type of heat treatment do I require. If I require an annealing treatment, then I need to cool in a different phase, or if I need a quenching treatment, then I need to cool in a different phase. So this is heat treatment thermal cycle. This is your welding thermal cycle, weld thermal cycle. So here this is your temperature and this is your time. One can easily understand in heat treatment the heating is slow and progressive and holding for some time, that is called soaking. Holding for some time, cooling with different rate, which decides the type of heat treatment do I require. Similarly, the welding, the heating is rapid and holding is in a small time, and it is being cooled to room temperature with very minimum time. So this makes the weld metal and heat affected zone will have to achieve a different microstructure which is not related to the heat treatment process. So now we have understand that in weldment there is a small portion of the parent metal which is being highly affected by the heat of the welding process, because the amount of heat which is being deposited in the fusion zone has to be transported towards the parent metal. There is no other go. So due to that heat transport, a part of the parent metal is to be highly affected by the heat. That is the reason this zone of the parent metal is to be called as heat affected zone. So now can we say all those kind of materials irrespective of the process selected will have a same kind of morphology in this heat affected zone? The answer is quite simple, it is no, not possible, because we have different kind of materials. Some materials will behave with respect to temperature with different phase transformations. That kind of material shall be called as allotrophic material. So other material may not have such a kind of phase transformation or different property, different crystal structures with respect to different temperatures. And some material will behave in a cold work condition that may not have require any type of heat treatment. They may not respond for heat treatment. So such a kind of material, when it is being welded, will behave in a different way in the heat affected zone microstructures. And some materials may not necessarily to have a different kind of temperature properties, temperature dependent phase transformations. And some of the materials will be heat treated to achieve higher strength, like your aluminum and other magnesium material will have a different property. They are strengthened by precipitate strengthening mechanism. So different material, we have 4 different kind of materials. All those kind of materials will have a different property in their in respect of welding. So we will see one by one. The material which may not have any allotrophic transformation will have a different microstructure in the weld and heat affected zone. It will have a coarse grain structure nearby the weld metal, and away from that it will have a fine grain microstructures. The underbead zone is understood, please. One has to note, nearby the zone you will have very fine grain microstructure, and away from that you will have band structure which is normally available in the rolled band structure. Since it is symmetric, I have drawn only one part of the weld joint. So this kind of microstructure is possible in non-allotropic material, allotropic transformation. And the other one which have allotropic transformation, that is temperature dependent microstructural changes. This is your fusion zone and this is your heat affected zone. Fusion zone, heat affected zone. This is your fusion zone, and in your heat affected zone you will have underbead zone, that is very fine grain microstructure. Away from that you will have a coarse grain structure, and away from that you will have very fine grain microstructure, and after that you will have a equiaxed structure. And then you will have another one fine grain structure, and then you will have pancake structure of rolled band. So now you can be able to observe the metal with allotrophic transformed characteristics. Will behave with 2 fine grain zone. Which is something different from the material which does not responding for any such a kind of allotrophic transformation. The other 2 which we have been discussed little earlier are the material may not respond for heat treatment, but that can be cold worked to achieve higher strength. That material will behave in a different structure in the weld metal. Even weld metal alone, it will have a very coarse grain structure, and away from that it will have again a coarse grain microstructure in this heat affected zone also. Away from that it will have a fine grain structure, that is due to recrystallization process. Away from that it will have a very fine band structure because of the cold rolling. The band width and band thickness will be comparatively smaller as discussed with the previous one. The band structure itself smaller because of the cold work. So now in the weldment itself, this fusion zone itself, a coarse excessive grain growth, and now you will have a grain growth region and you will have fine grain structure. So this comprised of excessive growth and then fine growth and then very fine grain size structure. So this is the difference between the annealed, cold worked annealed metal. When it being welded, it behaves in a different way. The other materials which do not have any kind of heat treatment or any kind of allotrophic transformation, but those kind of materials will behave in a different way because they are strengthened by only of precipitate addition. So aluminum is a common example for this one. Aluminium, copper, nickel, aluminium, copper, nickel. they may not have any such a kind of phase transformation during their heating from room temperature to the melting temperature. This is your liquidus temperature, and up to room temperature it may not have any such a kind of phase transformation, allotropic transformation, but these materials are strengthened by the heat treatment process alone. This is the normal range of aging temperature, but it will behave in a different way. The structure of your weld metal will have a different size microstructure. This is your fusion zone, but in the base metal, that is in the heat affected zone, it will have a precipitate free zone. There is no precipitate, free zone, and away from that you will have a coarse precipitates with a matrix, and apart from that you will have very fine precipitates which is in your parent metal. So precipitate free zone and coarse precipitate and fine precipitates. Now one can able to understand what happened in between the welding and during the heat transport. The part of the material which will experience a very high temperature, that is up to liquidus temperature and below solidus temperature. So in this part of the metal will experiencing a very overaging, that is overaging. Due to overaging, the material, that is alloy elements, will be available in solid solution. The alloy element will be in solid solution. That is the reason why this region is available with no precipitates. And apart from that, this zone of the metal will experiencing a very high temperature which is just below the solidus temperature. That is the reason why the precipitate available in this region is get coarsened. So these two, combination of these two is your heat affected zone of the material which is being designed for precipitate strengthening mechanism. So this will also deteriorate the property of the weld joint. So until now we have been discussed 4 different kind of materials with respect to its strengthening mechanism, with respect to its various morphologies. Now we will see what is the strengthening or transformation hardening effect with respect to the materials perspective. So for our discussion we will take the part of your steel and the transformation hardening of low carbon steel LC, LCS and mild steel MS. This is your weld metal, and away from that you will have a partially melting zone which we have been discussed little earlier also, and apart from that you will have a heat affected zone. This is your normal joint. But when only considering the iron carbide equilibrium diagram, we will put for our mild steel is concerned various regions D or A, B, C and D. So with respect to this, since this is a mild steel, 0.18% carbon is evident for these steels. Now we will draw the cooling curve. This is your cooling curve. It may be available with this region A, and this is the location of B, and this is the location of C, this is the location of C, and this is the location of D in this diagram. So now definitely the location A will undergo a very high temperature which is just below the liquidus temperature and above the peritectic temperature. The location A is achieved peritectic above 1492 to the melting temperature 1539 degrees Celsius. And location B is experiencing a temperature in the range of above 912, that is above A3, above 912 to 1492 degrees Celsius. And location C experiencing a low temperature which is above A1 but below A3, above A1 but below A3, that is 727 to 912 degrees Celsius. And location D is below A1 degree, below A1 temperature, that is just below 7 to 7 degree Celsius. Now with this temperature range, one can able to suspect, one can able to predict what is the initial microstructure during heating and cooling. So from the aid of this diagram and with the ion carbide equilibrium diagram, one can able to understand what are the initial microstructures of those region. So the region preferably A will have a partial grain, partially melted region. This is due to your weldment will have a partially melting. This partial melting region will act as a nucleation for the growth. So it will definitely undergo a high temperature, that is liquid state, it will be available, atoms are free to move, and then it will get combined to alpha, that is delta and liquid, delta ion with liquid, then it comes down to gamma, and then you will have final microstructure like this. So that is the reason you will have a very fine grain structure. And coming to the location B, it will be available at above A3 temperature. So it will have a complete gamma structure, all are gamma, then when it is being cooled to room temperature, gamma has to transformed as alpha and Fe3C. But at the same time, that is very high temperature in a range of long range of time. That is the reason why we can able to have only coarse grain microstructure. While the location C, it is being subjected to the temperature range between 912 to 727 degree Celsius. So it will have a dual structure of alpha plus gamma. So we will have the structure like this. So now alpha has no other go, even it comes down to room temperature also, it will stay as alpha. But the gamma ion, gamma grains 1, 2, 3, this has no go, it will not be stay as it is gamma even if comes down to room temperature. It again has to transformed as alpha plus P, alpha plus P, alpha plus P, alpha plus P, alpha plus P. So now there is a partial grain refinement in the gamma grains alone. So this is the reason why at the zone Z we have, at the zone C we have a partial grain refinement. Partial grain refinement. So the region A will be experiencing a very high temperature, the grain growth is evident. The region B, it will have a longer gamma phase transformation and it is being cooled very fastly compared with the location A. That is the reason why it will have a fine grain microstructure, and the location C will have a partial grain refinement. This is due to the existence of dual phase structure in the temperature range between 712 to 727 to 912 degrees Celsius. That is the reason why we can able to achieve a partial grain refinement. This is how the mechanism of partial grain refinement is being achieved in location C. And coming to the location D, it is the temperature range in between location D, the temperature range in between less than 7 to 7 degree Celsius. That is the reason why there is no phase transformation is being evident in this region. So this is the HZ of my steel metal, which is of our real interest of today's topic. It is having 3 different kind of microstructures. One is coarse grain, and the other one is fine grain, and the third one is partial grain refinement. So all the 3 kind of microstructures constitute your heat affected zone of the well metal. So this kind of complex and composite microstructure will definitely have a direct influencing over the well joint property, because joint consists not only this fusion zone but also with this underbead zone and your heat affected zone. So in heat affected zone itself we have 3 different kind of microstructures: coarse, fine and partial grain refined zone. So this is how the transformation hardening effect of this low carbon steel and mild steel were achieved. Now we will see how the transformation hardening of medium carbon steel and high carbon steel is achieved. In the medium carbon steel MCS or high carbon steel HCS, even the steel starting room temperature microstructure itself, it is having pyrolytic structure. It is having pyrolytic structure. That means it is having alternate lamellae of alpha plus beta, alpha plus Fe3C, alpha plus Fe3C, alpha plus Fe3C, alpha plus Fe3C. So even it is being heated or coming to the room temperature, it will definitely end up with again alpha plus Fe3C in the heat affected zone or even for well metal. Well metal is primarily depending on the type of filler material and process parameter which I am using. And coming to the well metal, which is having a different layers. Weld is being deposited with respect to different layers. Which is deposit to fill the layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. So now the heat affected zone of the first layer will be highly affected by the heat affected zone of the second layer. Similarly, the second layer's heat affected zone highly affects the welded deposit of this first layer. This is your original welded deposit. This is the heat affected zone merging. So now it is unavoidable. There is again a heat affected zone here. This is also a heat affected zone, and this part of the metal is also being acting as a heat affected zone. So when we are considering the multi-pass welding, for multi-pass welding, we are not have any chance to avoid the heat affected zone will have in the well metal itself. So it will directly influencing the property of the well metal or well joint. So heat affected zone is nothing but a part of a parent metal which is being affected by the heat of the welding process. It does not involve the process of joining of my metal, but at the same time the part of the parent metal is affected by the heat which is being transported towards this parent metal, and due to this a part of the parent metal will obtain a different kind of microstructures. Due to the different kind of microstructure obtainment, the property of the joint is highly affected or highly influenced. So we need to understand the heat of failure zone and its characteristics. Thanks for the patient listening.